So we will begin with a quick introduction of the domain, which is extreme multi-label classification. So extreme classification, also known as XML, is a rapidly growing research area in machine learning that deals with multi-label problems, which involves a large number of labels. The number of labels in these problems are can go up to billions, and this has a lot of applications in various fields like NLP, computer vision, and bioinformatics. Most importantly, it is being used as a new approach for industrial applications like ranking and recommendation, where it provides advantages over the traditional methods. Several search engines like Bing have used XML in their ad recommender systems, as well as Amazon has used it for object tagging and several other applications. So why machine learning is different from other domains is due to these reasons. The first is that the number of labels is very large, and this implies that application of simple classification methods are not possible as they become intractable. This is because the possible space for possible solution space is exponential. More specifically, it's 2 raised to L, where L is the total number of labels. Secondly, there is a very large tail label distributions, which require the model to learn with smaller amounts of data for the tail labels. This may often require few shot learning or for prediction of these tail labels. Further, a lot of the industrial applications, for example, recommender systems and advertisement, search, and these applications require very fast prediction time, which makes a lot of methods simply unscalable. So the deep XML framework is a method which utilizes deep learning effectively in extreme classification. The framework divides the algorithm into 4 modules. The first module is of intermediate feature representation learning, which involves learning intermediate representations for features which are as close as possible to the final representation. These final representations will then be used for training the classifier. The second module involves label shortlisting using negative sampling, which is performed on these intermediate features. So negative sampling is performed to find a smaller set of labels to search within, because searching within all the labels is intractable. The third module is based on transfer learning, which is used to obtain the final feature representations from the initial feature representations learned in the first module. And finally, in the fourth module, the final classifier is learnt, and this classifier uses the feature representations, final feature representations learned in the third module, and the negative samples which are learnt in the second module. Finally, an extra supplementary module called the re-ranker is learnt in addition to the original classifier. This is to improve the accuracy of the model, and it can be used with several possible goals in mind, such as removing misclassification due to some inherent assumptions in the model. So now I will give a basic introduction of our method, which is LightDXML. So LightDXML improves upon deep XML by using label embeddings instead of feature embeddings for negative sampling, and also it iterates cyclically through 3 major phases. One being proxy training of label embeddings, second is the shortlisting of labels for negative sampling, and finally the final classifier training using the negative samples. So this is the algorithm for LightDXML, which involves the following steps. In step 1, we map each feature to a metric space using a weighted combination of embeddings. we in the second step we map each label to the same metric space using a label encoder. A shortlist is then created based on these label encodings to allow finding the top k closest labels. A final classifier is then trained using this shortlist and the feature representations. Now these steps 2, 3 and 4 which involves finding label encodings, training a shortlist and finally training the final feature representations and the classifier. These steps can be iterated until a satisfactory condition is reached. For example, validation accuracy is maximized. And finally, during prediction, the prediction is done using a combination of the output from the shortlist and from the final classifier. So this diagram illustrates the light DXML algorithm. First, you start with the features and the labels. Here, during training, these labels go into the label. These features go into finding the label embedding in the same metric space. This is then provided as input to the shortlist, which learns the data structure. Finally, this shortlist is used to train the final feature embeddings, which is basically the final embeddings used for the classification. And this loops back to the label encoder, and this happens till it converges. And during prediction, on the other hand, the features are provided directly to the final classifier, and these labels are also used for prediction. These are combined in a linear way using different weights to achieve the final output. So what are the advantages of using light DXML? The biggest one is that the negative samples are updated several times due to the cyclic training procedure, and it makes the final shortlist more accurate, thus making the final classifier itself more accurate. On the other hand, in deep XML, since the shortlist is trained only once using the intermediate representations, the final representations might have produced a different shortlist and might have led to potentially worse results. This also alleviates, so our method also alleviates the need for a separate re-ranker module, which leads to reduced prediction time and model size compared to state-of-the-art deep XML approaches. So our experiments demonstrate that light DXML outperforms most comparable extreme classification methods, not only in precision and propensity scores, but also in terms of prediction time, which is an important factor in extreme classification applications such as ranking and recommendation. Testing on larger data sets also shows that the method is scalable, where many deep learning methods could potentially fail. In conclusion, light DXML is a faster and better method to perform deep learning based extreme classification. Several new methods have tried to learn label embeddings from label metadata, which is not used in light DXML because it is kind of situation specific that label metadata is available or not. But in case it is available, it can also be easily incorporated in the light DXML algorithm while learning the label encoder, and this will also significantly improve its performance. Thank you for listening to our talk, and hope you have a good day.